So, let us begin then trying to understand the mathematical structure of this additional term. So, to help us to do that, it helps to really remind ourselves of the meaning of all of the individual pieces that go into this so that we can try to manipulate the underlying mathematical expression of the law. So, just to remind ourselves what this term actually is trying to do, the components that go into it, you will recall, are that we have some sort of an origin somewhere. I'll just draw it as an O here. And the whole purpose of all this is to calculate the magnetic field at some location R. So I'll draw a little vector giving me my location R. And what we're looking at when we're summing over I are contributions coming from individual particles, which are sitting at locations Ri. But the whole point of the magnetic field discussion is that this particle I, with charge Qi, is traveling along with some velocity. Its location in space, which we've been calling R sub I, therefore actually is some function of time t. And it's the derivative of that function of time t that tells us about the velocity of the particle. So let me draw a velocity vector here, and that velocity vector v sub I is actually equal to the time derivative then of the location of that ith particle with respect to time t. So then what we are really saying when we are writing down this electric field at location R is that the electric field there, notice, isn't something that stays constant in time, because the whole point is that this particle is moving with a certain velocity. So that electric field depends on the location R, but it also depends upon time t in a very special way. Namely, it looks like Coulomb's law, where I've got the charge of the particle, I've got the location where I'm measuring the electric field, that's this location R, but I need the displacement vector from that to the location of my particle, R sub I. This difference vector is what I'm computing, but notice R sub I is something that's changing with time t. That's why the electric field itself is changing with time t. And then if I keep true to my Cartesian form, you can write this in any form you want. I have to remember I've got my 4 pi epsilon naught, and then of course I have this displacement, R minus R sub I, which depends on time t, and that whole quantity becomes cubed then down in the denominator. Now, this is the underlying mathematical structure of what we're trying to do. What I've just written down here is something that we're going to be working with in detail. As I've written it right now, though, this is quite a mouthful or penful to write down. So let me just define this right now as a shorthand. This is some function that we all know, and notice that the function itself is a function just of this difference vector between the location where I'm observing the field and this time-dependent location of particle I. Very good. So now that then raises the question, since we understand what this structure is, what actually is this term? It has some interesting features to it, and that's what we're really trying to understand. What ultimately is the value or meaning of this minus vi dot del of E sub I? Now, that quantity that we have up here, of course, it depends on position, r, and also time, t, of course. What is that thing? Well, in our shorthand, of course, that's minus vi dot grad f, where f is my function that depends on the difference between r and r sub I at time t. Now, let's try to relate all of our quantities here to see if we can find some identity, to put a better meaning on this quantity. Now, the velocity v sub I, as we've already noticed, is equal to the time derivative of r sub I. So that's a very interesting structure because I've got r sub I inside here also. So let me rewrite this. The dot product, of course, is commutative, so I can write this in any order that I want. I'm going to write it in this order because it's going to help us don't forget the minus sign. It's going to help us maybe understand what how to interpret this quantity. So I've got the gradient of f of r minus ri of t. So that's the derivative of f with respect to r. The gradients are always derivatives with respect to position, right? So I could write grad with respect to r just to emphasize that. And then, so I take the derivative of f with respect to r, and now I dot product with v sub I, but v sub I is the derivative of r sub I with respect to time t. Now that's kind of interesting now, isn't it? This looks a lot like the derivative of f with respect to its argument times the derivative of its argument with respect to time t. That's starting to sound a lot like the chain rule for derivatives. This looks like it should just be the time derivative, or related to the time derivative of f with respect to time t, because to do that we would take the gradient of f with respect to its argument and then multiply it through a dot product with the derivative of the argument with respect to time t. So let's try that. Let's see if that's going to work out. Let's try computing then the time derivative d by dt of some function written out where its argument is in the form of some fixed position r minus some time-dependent position r sub I of t. Now, if I were to do that, then I'm going to write this out in component form to try to understand the identity better. That would be the time derivative then of f, where the x component that goes into the argument of the function f is just my position x minus the x position of my particle at time t. And then, of course, I'm going to have y minus the y corner of the particle at time t, and z minus zi at time t. And I'm now going to take that derivative following the chain rule, and we know how this goes for partial derivatives, right? It is more or less what we've been saying. You would have the derivative of f with respect to its first argument, which is going to give me df dx. And then you multiply that by the derivative of the argument with respect to time t, which will give me minus dxi dt. That second derivative, notice, is a total derivative because the position of the particle depends only on time t. Plus, then we would have the partial derivative of f with respect to its second argument, which is the y coordinate. And then the derivative of that argument with respect to time t gives me minus dyi dt. And if you're looking at the structure that's coming out, the z component, of course, is going to do the same thing. Partial f partial z minus dzi dt. And what we're looking at now then definitely looks like some kind of a dot product, right? I've got these x coordinates multiplied together plus the y coordinates multiplied together plus the z coordinates multiplied together. So I can write this as a dot product. The first vector must have components partial f partial x, partial f partial y, partial f partial z, and that is precisely what we call, of course, the gradient vector of f. The second vector has these components, minus dxi dt, minus dyi dt, minus dzi dt, and that vector, when I put it all together, these are clearly just the x, y, and z components of the velocity of the ith particle, so that's dotted with minus vi. So it looks like, actually, this whole thing has worked out for us very, very nicely. This is exactly what we had written down here up above, even including the minus sign. This is just minus grad f dotted dri dt, because dri dt is, in fact, just the velocity. I've just pulled out the minus sign and used what I know about the velocity. So therefore, we know that this term is just it looks just like this, and when we trace our equation backwards, it's just the time derivative of this function f. So, therefore, what we find then is that this additional term that we're trying to understand, which was our mu naught epsilon naught sum over all the particles I, this goes all the way up here, right, to this mystery term. I've got the mu naught epsilon naught sum on I minus vi dot grad ei. Well, minus vi dot grad ei, we've just proved, is equal to the time derivative of ei. So then we have that that is minus vi dot grad ei of r. We just proved that's equal to mu naught epsilon naught sum on I of the time derivative of this thing we called f is vi dot grad fi. It's the time derivative of f, but f, recall, was just defined here as being the field from particle I at location r at time t. So that's d by dt of ei of r and t. But now that clearly is something we can really get a handle on, right? Because what we can do next, of course, is we recognize that this is mu naught epsilon naught times a sum of time derivatives. But the way derivatives work is the derivative of a sum equals the sum of the derivatives. So I could pull that derivative out, d by dt, a sum over all the particles in the system, the electric fields that they would create at location r at the given time t, and this being the sum over the electric fields provided by each of the individual particles. That then is just the total electric field in the system. So now we have something that looks very much like a fundamental equation. So this extra term was mu naught epsilon naught times simply the time derivative of the electric field, partial time derivative of the electric field at given location and time t. And then we can put the whole equation together. So what we've just learned is that the curl of the magnetic field has this very simple form in terms of local connections to fields and currents. The first term, recall, is our Amperes law looking term, is just mu naught times J, plus then the term that we've just been working with. So what we have then is mu naught times J, the current density at the given location and the given time t, plus then this additional term, which tends to be small, mu naught epsilon naught, but we'll see later it still can be important in certain circumstances, times then this time derivative of the electric field with respect to time t, where the electric field, of course, depends on location and time as well. And this is actually the full version, unapproximated, of Ampere's law. And we'll put a box around that. Now, the second term, we will talk about it more in future discussions, but this second term here has a special name, and we'll come back to that. That's something called the displacement current. It's a long story why it has that name, but what you can see is it certainly adds into the equation somehow like some kind of a current density. So it sometimes in the equations acts like a current. So that's where it gets that name, displacement current. And of course, just to emphasize, that is usually small.